do that. Alright, I'm going to ask for your attention to come back up here. Hopefully you've had time to draw your orbital diagrams. I'm not quite done, but here we go. Silencio, por favor. Silencio, por favor. Okay. So, on your first one, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Thumbs up if you got the electron configuration. Alright, I did that blindly, so it doesn't look too bad. Better than somebody else's handwriting. Okay. 1s2, 2s2, 2p6. There's 3 orbitals there. I did this blindly. This was a little bit bad, but there's 6 electrons total. 3s2, 3p6, 4s2. What is this supposed to be labeled? Okay, so 3d, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, right? So there's a total of 10 electrons in D block. And then what comes next? How do I draw that? 3 lines, calling them all collectively 4p, and how do I fill it? Up, 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 down, down, right? Okay. So looking at this, I saw a lot of papers. You guys were doing pretty good there. Who can tell me on the orbital diagrams what should be circling for valence electrons? Raise your hand. Izzy. 4s2, good, and 4p5. So how many total valence electrons are there? Who just circled the 4p's? Just, it's all right. Own the mistake, right? You will, because you don't see that 4p and then 3d and then way back you have that 4s. But if you wrote it longhand, you maybe saw it a little easier because there weren't so many diagrams in the way. So there are 7 valence electrons here. Yeah. The valence electrons. Give me a quick definition of what the word valence means. Raise your hand. Raise your hand. Yeah.
It's the one on the outside. So the biggest group.
So the highest period. There's another word for that though. Evan?
The outer shell of the atom.
Okay, I'll go with energy level or shell there. So the outer energy level or shell or thing number, right? So 1, 2, 3, 3, 3, 4, 3, 4. The 4s are the highest number. So that's your very outside energy level or very outside shell. So I'm going to say the 4th period or energy level. Okay, so there's 7 valence electrons, right? Raise your hand if you can predict what kind of charge it would form if it were to form an ion. Go for it. Negative what? A negative 1, 2, 3, 4. Why negative 1? So it's going to form a negative 1 charge, right? Because it will do what in order to get that negative 1 charge? Right, it will gain 1 electron to create 7 plus 1 electron. I don't want that to look like something else. Okay, so adding 1 electron would be 8 valence electrons, which we call octet. Okay, so all of this is just background information from taking your valence electrons up to the octet number, which would mean we gain 1 electron. You should be able to do that with any of these electron configurations. Tell me predicting their charge they would form if they were to form an ion. So looking at nitrogen, predict the charge it would form. Look at nitrogen in periodic table. Yeah. Negative 3, because it would gain 3 electrons to be like that of a noble gas. Look at calcium, guys. What charge would you predict it would form if it were to form an ion? Positive 2, because it would back up 2, meaning lose 2 electrons to form that of a noble gas electron configuration. So it's just the number of electrons that are changing. That's why we're not saying, oh, it's neon, it's argon. It's still what it is because our protons itself never change. All right, so goal for today, 20-ish minutes in periodic trends review, because we didn't quite finish running. It's Friday. You guys were dead as a doorknob. So I said, okay, we'll just finish it Monday. We're going to finish up some problem set 6 stuff, and then we're going to kind of start reviewing because I'm not available for tutoring until Thursday, because I have meetings all this week. Thursday is when you're going to start with your part 1 of your test. Friday is when you're going to finish up part 2 of your test. Right now I'm saying multiple choice Thursday, free response Friday, but I'll kind of see where we are, what we're feeling better with, and I'll get the one you're more confident with in first. Okay, so we're basically done learning everything. We're just reviewing, except for nuclear chemistry, which we're going to finish, or start a little teeny bit today, and finish up tomorrow. So nuclear chemistry with like alpha, beta, gamma particles, stuff like that. So this is just a big unit, so that's why I'm spending more time for review. Okie dokie? Okie dokie. Talk to the person next to you about what you talked about Friday. I specifically want to know the 2 factors we're going to use. Okay? All right, and 3, 2, 1, back to me. These are the two and most important terms that you will have to utilize and understand why you're using them when you're talking about PR trends. Because we all know this. We're like, boom, done, I know the trend, but I just don't know how to explain the trend. So you'll be able to get the questions where you're just like, okay, it's to the left or to the right or it's up or down. You'll get those questions quite easily because you know how to do this. But what you won't be able to do is comfortably is explain why that's the case, okay? So give me one factor, Kelsey. Okay, the shielding effect. And the shielding effect is a way of saying that inner electrons shield. Somebody complete this thought? Inner electrons shield, Austin?
Outer electron.
From what?
Oh,
shield inner electrons shield outer electrons from the nucleus's attraction, from nuclear attraction. Okay, and if you're adding to your notes, this is a little kind of a simpler way of describing it. And before I move on to you, Izzy, somebody tell me, is this a trend or is this a factor we're going to use to describe a group trend or a period trend? I heard a lot of people say it. This is like what we'll use to describe anything that's talking about up and down on a group. Okay. So what was the one that we mentioned before that, Izzy? Zeph. Can you tell me what that means? Zeph. Anybody? Yeah.
The more neutrons there are, the stronger the pull.
Not neutrons.
Protons.
Protons. So the more protons, the more protons,
The stronger the pull.
stronger the pull from the nucleus to the valence shell. Okay. So Zeph means nuclear. Anybody? Nuclear. Give me the whole thing. Effective charge. Okay, nuclear effective charge. Basically it's saying how effective is the charge of the nucleus at sucking in electrons and sucking them in and pulling them and shrinking them down closer to the nucleus. So how effective is the charge of the nucleus? Do you see how that comes together?
Yes.
At pulling in the valence shell electrons towards itself, towards the middle. Okay, so those are the two factors, and this one is going to be helpful in describing a what kind of trend, period or group. Period trend, and that's going from left to right. Okie dokie. So that's a quick review from there. So we did what two on Friday? What two trends did we talk about Friday? Atomic radius and ionization energy. What are the last two? And electron affinity. Okay, I'm starting with electron affinity. So the details to this, they all fall back to the two factors I just wrote on the board. Every single one of them is just explaining what they are and then giving a tad bit more detail. So electron affinity is still talking about like amount of energy, just like the ionization energy side of things kind of reference. But this is not the energy to make a cation. This is the energy needed to make an anion. So how does one make an anion? Austin? All right, so it's energy given off when one electron is added to the valence shell, valence electron shell. So sometimes that's a really good thing. Sometimes like, heck yeah, I want another electron. I can be like a noble gas. I can have, enough electrons to look like the electron configuration of a noble gas. Sometimes that's not a great thing because, like, for example, group 1. Does group 1 want another electron? No. It has one valence electron. If you get another, it's like, oh no, I'm not going to get rid of 2. It really just wanted to get rid of the 1 to be octet. So that's why you guys actually explored this already. It was a roller coaster of like high, low, high, low, high, low, high, low. You're like, missing load, this doesn't have a trend. I was like, look for the big broad picture. The general trend, which is still kind of iffy, runs the same direction as ionization energy. Okay, so they run the same direction. Before I move on to more about the definition and kind of how this works, does anybody know what affinity means? A liking for them. I have a strong affinity for chocolate. Okay, you guys remember that? My birthday's in like a month and some change. Okay, I have a strong affinity for chocolate. I will find it. All right, so this is basically like you love something, you want it. So some atoms want an electron, and sometimes they don't. That's why it has a wavering effect. But here's your general scheme, right? Where are the largest atoms? Largest.
Top right.
Right-hand radius, right? So then you go like this. These are the big ones. Where are the smallest atoms? Top right, okay? So if you were the nucleus, right? In the middle of, I'm going to call this atom 1 and this atom 2. If you were the nucleus in atom 1, how strongly do you think you could attract an electron that's like hanging out here? Not very well. Like, look how far away the nucleus is from this electron. It's got some distance to it, so it's not going to have a very good attraction for it. So it's going to be a low amount of energy that's going to be given off when that electron comes in, because it's not a strong attraction. But how about this one? How well do you think this nucleus could attract this electron? Very well, because there's not a lot of shielding in the way. So the size definitely plays a role. Compared to this one's going to be our medium. 1, 2, 3. Who would be able to best attract this electron that's hanging out here? 1, 2, or 3? 2. Okay, and then who? 3. And then who? 1. So the size matters. Okay, so the one that's the farthest away is not able to attract the electron. The one that's where it's very close, because there's not a lot of energy levels in the way, it's more easily going to attract the electron. Something else to think about, though, since I've drawn it this way, I wanted you to see the factors at play here. What factors at play across this period? What's the difference here? You remember the 2 factors we just wrote down for warm-up. Which one has a higher ZEF? Number 2. Good. This one, the ZEF increases this way, so it's got a better, stronger nucleus because it has more protons. Why is there a difference between 2 and 1? I mean, 3 and 1. What do you call those energy levels? What are they doing? Shielding the positive pull from the nucleus to the outside. So if you're ever describing things across a period, you're going to talk about the increased ZEF or lower ZEF, nuclear effective charge. And if you're going down a group, you're going to say more or less shielding. This is a little bit more wordy, right? This is the more conceptual side of things, but as long as you have this, you're 90% there. Okay. Last one, electronegativity. Write down your briefing there. Who's the person that has to like write down the thing to know the thing? Like I have to write it 5 times to know it. All right, keep writing. Raise your hand if you're I hear it, I know it person. Raise your hand if you're not sure. Okay. So you should try different things. Don't just try to listen, because then you may not be getting what you need. I usually make people take a learning survey. Look at yourselves very well. Because you might think you're on Okay, so some of you are still writing there. Actually, I'll pause for a second. This runs with the same direction as what other trends? Ionization, electron affinity. So this way, right? So just adding another one on there. Okay. So this definition isn't just like, hey, I'm taking an electron or I'm giving it away. It's actually with referencing to bonding, or reference to bonding, which in this case, it's actually more along the side of the shared type of bonding, or the shared electron type of bonding, which is a covalent bond. So the definition of a covalent bond is just when two elements, or I'll say two atoms, share electrons to get their own personal octet. Because even if I'm sharing an electron, I still can count it as my own because I'm like holding on to it. I can still consider that a part of my octet. Just like if you were holding the same electron, you can consider that part of your octet, even though neither of us have it. We're just putting it between us. Okay, so with reference to this, the atoms or the elements on the periodic table that definitely want electrons read who? Who so desires electrons so much they're willing to steal it from somebody else so they can look like that of noble gas? Top right, okay? These up here, I'm gonna say like top right, but it's also like entirely group 7A. Group 7A are the halogens, right? How many away are they from octet? One away, right? They want to rip an electron from somebody else just so they can become octet, so they can be stable just like all the noble gases. So all of group 7A is willing to take on electrons, but some of them are more willing or greedy for electrons than others, and it's just simply based on their size. Who over here is the largest, the top or the bottom of group 7A? Group 7A, I'm going to make it really big. So these are smaller, these are larger, right? Because the atomic radius trends this way. So who, in thinking about their nucleus, right, who is able to attract an electron in a bonding situation better? Top or bottom? Well, top, because there's less shielding, right? There's no shield to block the pull of the nucleus on the outside. There's all kinds of shielding here. This poor little nucleus doesn't even know there's a life outside of its walls, right? Because there's so much shielding that's limiting the impact of taking on electrons out here. So that's why it runs up and to the right, not just clearly to the right. Another thought here, I'm going to talk, this was the shielding effect one, right? Because this was going down a group. What if I was talking about going this way? Let's draw lithium over here. Who's better at attracting an electron in a bonded situation? One or two? One, yet again, because it has, that's compared to this one, higher Zeph. Remember, Zeph runs increasingly to the right. That's because, let's just say I was throwing lithium and fluorine. Lithium has how many protons? 3 protons, and fluorine has 9 protons. So remember, Zeph is nuclear effective charge. The effectiveness of the nucleus's charge at attracting valence shells or valence electrons. So 9 protons is a heck of a lot better charge and able to attract outside electrons than 3 protons is. So this one is going to have a better chance at taking on more electrons, like in the electronegativity side of things. Who's okay on Zeph? Who can explain Zeph? I got one. Okay, if we're ever comparing across a period, you have to mention Zeph. You have to mention the number of proton differences here. If you're ever comparing down a group, you must mention shielding effect. Okay, I'm going to ask you guys some more of those questions shortly. Okay, so let's do some practice questions like you would be expected to do, like on a multiple choice question. Okay, so I can go back in a second. Okay. All right, so you guys do the first two. You got 30 seconds. It should be pretty fast. All right, 3, 2, 1. Okay. Anna, tell me between aluminum and boron, which, by the way, you got to know this periodic table, at least not like, don't have to memorize it by any means, but you have to know where things are, right? So you're not hunting and pecking for everywhere, forever. So aluminum and boron are here. Anna, who has a larger radius? Aluminum, because it's on your trick, right? It's lower down in the group, so it's got more energy levels. So aluminum is definitely larger. Anthony, for oxygen and sulfur. By the way, everybody, oxygen and sulfur is here. Sulfur, because again, it's lower down in the group, so it's got an extra energy level. Everybody together now. This one, sodium aluminum. Take a second. Can I get a consensus? 3, 2, 1? Okay, because, and I'll help you out with the explanation for this one. Here's aluminum, here's sodium. We're talking a period trend, so of course I know you can do the finger trick and you're just like, hey, it's sodium, but if I ask you to explain something, you would say sodium has a higher or lower? Lower Zeph, so it stays large because the attraction is not as, and doesn't influence the sizes too much. This one has a higher Zeph, aluminum has higher Zeph because it's got more protons, so it can attract its electron shell. Last one, oxygen and fluorine. Take a second. Oxygen and fluorine. They're here. All right, 3, 2, 1, answer. Oxygen with a sodium. Oxygen, because oxygen has a lower Zeph. So this one has 8 protons and fluorine has 9 protons. 8 protons does not pull on its valence shell of electrons very well. All right, keep going. Do the first 3. First 3. All right, 3, 2, 1. Pause your conversations. Okay, so everybody first was like, okay, I know that it's the left hand, and ionization energy low means is that up here or down here? Lower. It's lower, right? It's closer to where your palm and fingers touch. All right, back with me so I can make sure we're clear. Calcium, calcium. Zinc, zinc. Who has a lower IE? Calcium, because it has a lower Zeph, right? It's further to the left if you were just thinking that way. So that means that it doesn't have a strong attraction for its valence shell, so it's like, sure, you can have that extra electron, I don't really need it. There's not a lot of energy that's required to pluck it from my outside. But zinc's like, heck no, I want my electrons, I've got a strong pull on them. You're going to really have to fight me for it to get those electrons, which is what the energy aspect comes in. Chlorine and iodine. Who has a lower lower ionization energy? Okay, because on your hand trick, it's lower down in the group. So iodine has a lower IE because it has more shielding, because it's like shielded. It doesn't really attract its valence shell very well, so it's quite easy to take electrons from its valence shell. So this one's iodine. Now this one, I'm sure you guys are like, Who was a little confused on this one? A couple of us, okay. So here's aluminum, and here's tellurilium. So here's the trick on this one. If you ever have to choose between something that's not in the same group and same period, usually the group different makes the group issue makes a bigger difference in the overall characteristic. So I'm going to say, since this one's lower in the group, right, than this one is in its own group, the lower one in the group is lower in terms of ionization energy. So when you're fighting between two that are not in the same period or not in the same group, the one that the group trend trumps it all, okay? So that's why I'm going with tellurilium as being the lower ionization, because in terms of lower ionization, it's the one that's lower in the group.
Right, so lower group equals.
Lower in its own group, like versus aluminum in its own group, lower in its own group means it's got the lowest ionization energy between these two. So the question, of course, would drive how we think about that. Yeah. It kind of depends on how the question is phrased. So like in this question, instead of saying IE, I could have said who has the largest radius. The largest radius, it would be, let's see here. Did I say largest radius? So it would be the one that's got more rings, so it's actually still lower in its own group. Because going this way, between tellurilium and aluminum, there's not a big proton difference necessarily, but it's going to be the more rings makes it bigger. So the group, again, wins. Okay? Okay, let's do a couple more practice and then I'll set you free. Let's just do calcium and gallium, and then, hold on, I'll take the other one in a second. What's the other one? And this one. Just those. Well, calcium, the first example. Do this example and this example. All right, 3, 2, 1. Go. Okay, so gallium is here, calcium is here. Everybody who's got the higher electronegativity. Gallium, right? It's even closer to noble gases, so it's more eager for electrons, which, remember, that's a part of the electronegativity definition. Okay, now hydrogen and oxygen, I hear some of you guys going, it's this one. Can I get a choral response? 3, 2, 1. Ooh, I heard both. Ooh. Okay, if you're more confident, you gotta be louder. 3, 2, 1. Oxygen it is. Okay, so let me tell you why. Here's oxygen, here's hydrogen. So we have a kind of a weird situation, because this one's at the top of its category, right? So it's pretty high in terms of electronegativity. But this one's not only close to high in its category, but it's also even farther to the right. So it's got two things going for it. It's high and it's to the right. So definitely this one has a higher electronegativity because this whole corner over here is closer to the noble gases, so they're more eager to take on an extra electron if they could, even in a shared situation like a covalent bond. So this one is going to be the highest because it has not only it's not only highest in the group, but also farthest over in the period. Okay, so think about the definitions as well. It might help you a little bit. All right, let's go through some problem set 6 stuff. Okay, you guys have a problem set 6? You're supposed to start it. This information will help you with the most metallic and most non-metallic aspects. I'm going to give you guys just a couple minutes there. You might want to write some of this down if you need to, or just take a picture. It's going to be useful for that table. Okay. Do you want me to pull up problem set 6? Yeah. Okay. This is helping with that metallic category. Metallic. I can write that over here. I'm just going to draw a picture, actually. Non-metallic. Metallic. Alright, I'm going to pull up problem set 6 then. All right, can I take this down? I got Savannah saying yes. Anybody else here? Okay. I'm thinking the table is where you need it, so I'm going to leave it at the table for a minute, okay? There you go. I'm giving you guys like 5 minutes to ask me questions where you need it right now, okay? You should have already started to figure out where you're going with it. Raise your hand if you have a question on 1.6, guys. So basically, yeah, we do all of that. I mean, oh no, sorry. Wish this would go away. It increases going top to bottom, so I think it might be
For you do the same thing for all of them except for so you do the same. So that's probably why for like.
All right. Any remaining questions that you need to answer before we wrap this? Because you guys can finish what you need to later. Ask me now for a coach piece. Anthony, what was one of your questions up here?
How do you know which one's forming color compounds?
And what kind of compounds are colorful?
The transition.
Transition metals, right? So if you didn't know that, now you should be able to pick out the transition metals. Somebody else asked me this. How would you guys determine who's conductive? Anybody that's a metal, right? So you should know your staircase of metalloids fall. And then I think you guys, since you know your group categories, I think these will be easy enough to find. Okay? So this will be our last main activity for the day. Before I move on from this, I didn't actually tell you what was important here. The metallic characteristic doesn't mean just like, oh, I'm shiny, I'm metallic. It actually means that its electrons are kind of loosely held, so they're likely to lose electrons. So I want you to remember that. Metallic means likely to lose electrons. So then, counter to that, what does non-metallic mean? Right. So they have a high likelihood of gaining electrons if they're considered non-metallic. But just memorizing those as single factoids don't really give you the guts behind it. That's why I was just mentioning they follow the same trends as atomic radius, which is low and to the left, and then non-metallic follows that of like everything else, which is high and to the right. So it helps fit them into the correct trends if you understand the trends, and that gives you some influence on how they change their electrons up. All right, so metallic means likely to lose electrons, non-metallic means likely to gain electrons. Good. All right, so I handed you guys this day one, when you picked up all your stuff for unit 2. Can you guys find this little chart in your stuff? Yes, the answer is yes. One answer. Yes, we can find it. I'll see by the extras. But I don't think I do. Right. I want you to stand up if you find it. Stand up if you find it. That way I mean you guys have found it. Stand up if you find it. Oh man, I didn't think that's with you. So some of you guys got straight sheets and some of you guys got just two to a sheet. Alright, so sit back down for me. Sit back down. Alright, so you're going to be moving here in a second, but I want to tell you what the goal is here, okay? You're good. Alright, eyes and ears up here. So this is kind of an interactive review. And so what I want you guys to do is, on the back of the paper that you're working with, it can be on the single sheet or it can be on one big sheet. On the back of it, what you're going to have is a thick grid, and that grid matches your Atoms bingo card. Basically is what I've done here. You see Atoms/bingo? It's like the same number of letters. Okay. I figured someday you would think on that. Okay. So you've got this little grid on the back, right? So you can just look through and sketch the same grid and put atoms on top, because we're cool, okay? And as you guys review, basically, the idea is if you can teach somebody something, you know it. If you can't teach it, you don't know it. If you can use the correct vocabulary, you know it. If you don't know the words to use because you haven't practiced it in your brain enough, you don't know it. So, in order to force yourself to get in a situation where you can teach somebody else, you're going to be doing this quick review. And we'll finish it up tomorrow, so you're going to try to get at least one bingo. Bingo can run horizontal, vertical, or diagonal, right? or I'm in Adams, but I was trying to make sure you guys were picking up what I was putting down. So by the end of this, you know, we're going to do one each day so that your brain's kind of kicking in like, oh, I need to know this. I've seen this again. I can teach this. But basically, you have to go up to a friend. So you're basically going to have to go to every person in the room. So I'm going to go to Jasmine and say, Jasmine, what can you answer on my sheet of questions? And she might say, hey, Enlo, I can tell you how wavelength and frequency are mathematically related. So she explains that to me. I'm like, active listening, eye contact, and then she's going to sign my paper in that section. So that's where over here? Under the T, right? So 2T. So she'll put Jasmine, whatever. You just put your initials there. And that's it. I'm not, unless I hear you guys getting off topic, I'm not going to have you write down anything because we've done enough writing and practicing on our own. I want you to orally be able to discuss something with confidence. Does that make sense? So once Jasmine tells me something, I can't do like pace by. She's going to say, Enlo, what can you tell me? And so she might strategically ask me, hey, I only need one more in this Adams, so you might ask me the one question you want me to answer. Now, if I can't answer it, of course, ask me another one. So you're going to have to talk to every person in the room, basically. You can't ask the same person more than one question. Coolio? Anybody? Say again? No, there's no free space. You see that? Okay. And if you understand, give me a thumbs up. You drawing your quadrants on the back? All right. They sign on the back. Okay. They sign on the back. Get going. Let's go. Get up. I'm going to give you guys 10 minutes. Can you? Because I think I gave all mine out. If I can just leave it here. They're all fun. I'll just leave it here. It's going to be a little hard to read, but you can keep looking up here.
Okay, I can do this for you. And hope it's not I honestly forget that, so you can say I'm working on a problem. I can't even remember.
Get your butts out of your seat. Get your butts out of your seat. Move your body.
It might be wrong.
I can do the regular That's all right. That's all one in person. And you it has 11 electrons and one valence
Alright, give me on your hand how many signatures you've got.
I have like 2.
I want to do one more. Alright, I'm going to give you 3 more minutes. Get 3 more. Get
3.
All right, 3. Come back to desk. 2, come back to desk. 1, come back to your desk. 0, you're back in your desk. Not yet. We're going to do 3 of them. We're going to do 3. That's good. All right, so we have about 25-ish minutes left. So here's the last assignment that I'm going to give you guys today, but then I'm going to let you have some freedom and choice, because I know some of you guys, who's 90% done with their projects that are due this week? Just asking. That's all right. Loud and proud. You guys are, yeah. All right, hands back down. Who's 50% done? I don't need sound effects. I'm just asking. Okay. So what we're going to do now, and a lot of you guys. So this is our introduction to nuclear chemistry. Instead of doing a traditional reading guide, because some of the stuff in the reading guide or in the chapter for nuclear chemistry is just not relevant to what we're going to learn. It's actually going to be something a little bit more interesting. And I'm going to pull that up for you here. So it's called close reading. No, it's not a movie. Okay. Sorry, I know you're addicted to the digital technology. Here we go. All right, so it's called close reading. And a lot of you guys have this on your Adam bingo. You guys see that on the right-hand side or left-hand side for you guys? Who does not have that? All right, for some of you, I had different size copies because I was trying to copy more than I needed to. Who does not? One more time. Raise your hand if you don't. All right, so what I've done is I've modified one thing, but this is basically a way to have you read closely, aka close reading, right? Something that's totally new to you. So I've got 3 different articles, and each person will have 1 article, and then you'll get back tomorrow together in groups of 3, 1 with each of the articles, and you'll share about what you read. But it's not just like, hey, let me read this article to you. It's going to be based on what you guys did individually. So here's where your points come in, because you guys will turn this in so I can actually look at it a little bit more harshly tomorrow. When you're reading, and you're close reading, you have to do a couple of things. Just like you would annotate a textbook or reading in English, annotate with it. If you want to do sticky notes, that's fine. If you want to highlight, that's fine. If you want to underline, that's fine. But try to do a mixture of those so that you're kind of utilizing all your skills. So underline or highlight keywords or phrases or anything that strikes you as surprising or important, or that raises questions. Annotations can also include margins in the text. Annotations or comments in the side of the margin that will be giving me some insight to what you're understanding within that paragraph or within that reading. And if you come into a word that you're like, I don't know what this means, just look it up, Google it, and add that definition in the margin. So I want a mixture of highlights, extra comments from what you're reading in the margin. If you want to put sticky notes on there, that's fine. But kind of mix that up a little bit. That's 6 points. Okay. So I need at least 6 quality annotations to get those 6 points. Okay. I'll show you what the reading looks like in a second. At the end, it says summary statement. So you get 2 points for writing a summary statement. It can't be any more than 25 words. Okay. So I don't need like a whole book on this. Just a summary statement. Somehow including the author, title, 25 words or less. That includes the main idea of that reading. And then at the end, you have a reflective statement, and the reflective statement is 1 to 2 sentences. I don't have a word limit on that, but it's going to start with like, I noticed blank, I saw this, I realized this, I'm not sure of this, I'm surprised about this. So it's more of a reflective statement. It's really easy, and there's actually most of my students like this more than reading guides because it's a little bit more interesting, and they ask for me to do them more often. So if you're in the first row, like Cole's group here, and grab this article. Okay, if you're in the second, so Mackenzie's area, and grab this article. If you're in the third, Callie's area, and grab this article. And I'll keep repeating, so I'm trying to get after this. Okay. So Callie et al. That means Olivia and Lady. You guys have this one. All right, and then Savannah's group, we're going to come grab it on the back. Nikki, the one on the side over here. Emily right here. And then we'll do every other one. First one in the back, the second one on the side, third one right here. First in the back, second. All right, back to me, back to me. You guys good? All right, so here's the deal for the last 25-ish minutes. You can either, 1, finish your article now. Sit quietly and read and get that thing knocked out. 2, finish our problem set 6. 3, work with your partners on your group project, but you need to be quiet because I have some people that are done and they'd like to move on to their homework. But what is due tomorrow? Problem set 6 and your close reading. But if you can't see the images, because I know the copier is not really friendly for some of those, I've linked them all here. Antimatter, origin of chemical elements, and like the sun one. Okay? So, you guys good? You know what you're doing? Go, do what you're doing. Okay.